Okay, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Hopefully you're all doing well. You had a good week. Ready to jump back into it. So as, let me see here. Let's share my screen. Let's make sure I can see the chat on this. Okay, and as has become our new custom, or hopefully I want it to become a better custom, in the interest of more interaction, feeling like I'm not talking to myself, I would request that you turn your cameras on, you engage as much as possible, so not everyone feels like they're alone out there. So I'd really appreciate it if you can do that. And let's actually jump into it. Okay. Last time we were talking about applications of Taylor series, went through a bunch of them. I also mentioned that the most important one is application number 5, but I'm going to talk about all of these guys because they're actually quite useful. And so we spoke about Euler's equation, very important. Glossed over the binomial theorem. I'll talk a little bit more about that. Computing limits, writing constants as infinite sums, and so on. So we looked at Euler's equation, which is this guy, which is muy importante. But I thought I'd show you something cool to show you that it generates this equation, which a lot of people believe is the most beautiful equation in all of mathematics. Includes all the important constants and operations in mathematics. And it's really cool that these guys kind of came together like this. We skipped over that, but we spoke about just replacing certain functions with their series version and how that can help us with limits. Also kind of ran over how we can represent certain constants as infinite series, and that might be really important for proving certain things. And I asked you guys to try these, so hopefully you did that. And we are pretty much going to start there. Wait, there is. Okay, so I think there are a couple of things I do want to mention here. So, okay, so let me actually put some things in here. Okay, on November 12th, 20, we went over the binomial theorem. Then came here. And so then we can move over here. So the binomial theorem is actually a little bit above. I'm just going to talk a little bit about that, then jump back down here, as well as I do want to just mention some PSAs, just to make sure, some public service announcements to make sure that we're all on the same page and we're we know what's going on. Okay, so homeworks for the rest of chapter 11 have been posted. Okay, so someone reached out and emailed to me and reminded me that I didn't actually post homework for the rest of chapter 11. So yeah, so that was my bad, very bad, Jhevon. And that's because for all my other classes, I set up the homeworks that I was giving them for the entire semester way at the beginning. So there are times when I remember that, oh yeah, for my Calc 2 class, I have to do homework. But then at some other point, I'll convince myself that I already did it because I did it for the whole semester, but really I'm thinking about all my other classes as opposed to this one. So I have to be a little bit more careful because ultimately I'm not even sure everything I'll be able to get to, what I'd want to skip over, and so on and so forth. So I'm kind of doing the homeworks for this class as I go. So every now and then I'll forget to post some homework. So the homeworks for the rest of chapter 11 are up. So we have done 11 sections at this point from chapter 11, and I've only given you homework on 2 of them. So yeah, that was no bueno. As a result, what I would say is no quiz tomorrow. Because you probably, chances are, haven't done enough practice to actually be ready for that, because Jhevon was bad and didn't give you guys homework. In terms of what to do tomorrow, I'm kind of torn. I don't know if I can just use it as an extra lecture period so we don't have too many new topics being crammed just before finals week. Because I think during like the last few sections that we're doing, a lot of new ideas are going to be introduced. None of them are going to be difficult. I mean, integration in series is by far the most difficult parts of these courses. But there's just, I guess there'd just be a lot of things. So I don't know. I might actually just take over recitation and continue lecturing. Or I don't know, have you guys like use it as a recitation period, but I don't know. It depends, like how usually when I ask you guys to have a recitation period, is it actually productive? Does it actually help you guys? Do you guys feel like you get a lot covered? Because if the answer is no, because a lot of times whenever that's the mode of recitation, it's kind of depending on how much interaction you guys have. So I don't even know. So that might be, yes, I'm actually torn. So maybe I'll make a decision tonight, and you guys can probably, I don't know, you can probably even vote on it, on what you'd want. So you just want a regular Q&A recitation tomorrow, or maybe I can just continue with another class? What do you guys think? Maybe
another class might be helpful.
Okay, so we can actually do that. I can actually just set up another Zoom link. I'll send it to you guys and we can have another class. So just to continue, because the plan is to finish everything we're gonna do on series today. So I'm gonna start getting into new material, and it's probably nicer to start it sooner rather than later. That's just what I think. So yeah, we can probably just do that. I will let Professor Golek know then. Okay, so no quiz tomorrow. We'll just we'll do an extra lecture. Look out for link. I'll send it through like the Jupyter grades mass email or something tonight. Okay, what else do I want? I just do want to remind you guys again to just pay attention to exam and final exam schedule for all your classes. So you know when my second test is going to be, and you have a rough idea of ever so often when the quizzes are going to be. It's always like on a Friday. Make sure you know this information for the rest of your classes. I also sent you the link to the final exam schedule. Make sure you know when the finals for all your classes are. Really start, this should have been done already, but if you haven't done that already, make sure you get it done today. Trust me, finals week will be upon us much quicker than you realize. You need to start mapping everything out and just coming up with a schedule, knowing when you're going to be studying for what needs to get done. Just start thinking about a general timeline of how you're going to manage finals week. Come up with a plan now. You don't want to be in finals week and you're all stressed out and you're worried and you're anxious and then you don't know what to do. You're just like, I don't know, I have so much to do, so little time. It's better that now, while you're level-headed and you're calm, you can come up with an actually logical way to get through everything. And then when you're in finals week, even if you're anxious, just execute. Just like, I already have a plan for what to do. I know exactly what to do. Today I'm supposed to be doing this. It'll help. So definitely actually make sure you know the schedule. What else I want to mention? Fill out doodle poll for next Friday. So we're having another study hall session tomorrow. I will send you guys the time and the link as well. But I also thought another one would also be useful. So the study hall thing, I think, was pretty good, but it didn't go according to plan. I mean, it was a lot of stuff to actually get done in 2 hours. So I figured we can break it into 3 parts. And so last time was just general plans, and a lot of things were theoretical. I gave examples when I could, but overall it was just very, very theoretical. At the end of the day, it's all in the application, right? And it's all, the devil is in the details. Most people know the right things to do, but they just don't know how to execute it, right? Everyone knows that we should be eating healthier and exercising more and sleeping more. No one does it, right? When it comes to actually applying it to your life, it's a whole different story. So that's kind of what I want to do tomorrow, just actually bring the theory down to earth. And then what I'd also like you guys to do is to actually try to apply these things that I mentioned. Don't just sit on it and tell yourself, oh yeah, I know. No, actually try to apply it. And then the following Friday, I think that study hall session, I'm hoping, can be more of like a troubleshooting thing, just like a general Q&A. You can say, hey, I tried to do what you said, Jhevon, and it didn't work, or I feel like I learned less, or whatever. Whatever issues you had trying to apply what I mentioned, we can deal with that next Friday, next week Friday, I think. So something like that. But we have to come up with a time that would be good for most people, so fill out that. I think that's all I want to mention. Oh, another thing. So note, in one of the homeworks, I believe in some homework problems in one of the homeworks carry 0 points. So there were some problems in the homework that are talking about some of the applications that I mentioned here that I said I won't test you on. I just put those guys in the homework just in case in the future I do it with one of my Cal 2 classes. But I put it as 0 credits, so you can skip it without penalty if you want. So there are some questions that ask you about the binomial theorem and some other things like that. So I'm going to talk about it, but I don't expect you can skip it if you want. I think you should know that it exists, but I'm not going to test your ability on that. So yeah, you can just notice in one of the homeworks, I forgot what section, I think it's 11.10, where there are like 3 or 4 problems in that where I put 0 points for those problems. And it means you can skip them. I don't consider them important. I'm not going to test you. Okay, I think now that's all the announcements I want to make. Any questions before we move forward on the class, or any general questions or concerns before we jump back into it?
On one of the homeworks that was already up, I'm pretty sure there's a question on the telescoping series. Can we skip that as well?
Yes, and I believe I saw that, and I believe I deleted it. So make sure you go back over that homework and tell me if it's still there. If it is, just actually shoot me an email and let me know, because I'll actually go in and delete the question altogether.
Okay, thank you.
Or I'll make it 0 points or something like that.
So I'm not sure I'll be able to make the study halls. Will they be recorded? Should we watch the recording?
They will. They're
Does that
not
work?
mandatory, but they're highly recommended. If you're not going to make it, especially if you're not going to make it, what I would say is you definitely want to be a little bit more interactive. So I would watch them after the fact, put them in practice, and then just try to make sure that you send me some sort of questions, so that since you won't be there, I can address your questions directly, even though you're not going to be there, and then you can watch the recording of me addressing your questions, I would say.
Thank you.
Okay. Yeah. So let's actually jump back into it. Let's talk about some more applications. Binomial theorem, pretty cool application. Not going to spend time on it. I do want to just talk about it though, because I always tell my Calc 1 students that, when you get to Calc 2, you'll learn how to expand a radical. And it's just, it's kind of bad if I don't even mention it now. So let me just mention that. So the binomial theorem is pretty much the guy that tells us how to expand binomials. So a binomial is just a sum of two terms. And when you raise it to a power, and the power is, and n is a positive integer, the binomial theorem tells you how to expand these, right? So the binomial theorem is what would tell you x plus y squared is x squared plus 2xy plus y squared, or et cetera. Or it can actually generalize. So it generalizes to this guy. It's the sum of these terms, where n choose k, this is called the binomial coefficient. This is what this guy is called here. If some of you have taken probability statistics, it also might look familiar to you, because it's actually also what's called a combination, the number of ways to choose k objects from n objects. But it turns out it's actually a number in the binomial theorem, for actually exactly the same reason. It's because you're actually choosing how many factors of x you have out of n factors, and so it has a very it's actually connected to choosing stuff from probability. So this is that. You can actually write that in terms of factorials, which we have here, so you guys know how to do what that means. So there's this number, and when n is a positive integer, this guy here is also going to be an integer, and it actually tells you what integer would go in front of which factor. So if you were to expand this, it'll be written out as just like x to a power y to a power times some coefficient. And this n choose k tells you what the coefficient is. For example, you can actually use this to figure out that x plus y all to the fourth would be x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth, right? So there's a theorem that tells us how to expand this. Another flavor to this is using Pascal's triangle, that tells you these guys. And so how you do this is you start off with a triangle of ones. So you start off with like that, but then you go to new lines, you start off with a 1, you add the two terms above to get the middle term, and then you end with a 1. So for the third line, start with a 1. 1 plus 2 equals 3. 2 plus 1 equals 3, and then I end with a 1. Going down one more line, start with a 1. 1 plus 3 equals 4. 3 plus 3 equals 6. 3 plus 1 equals 4, end with a 1. You'll notice here that this line, for example, it matches with the coefficients here. Notice the 1, 4, 6, 4, 1 is here, 1, 4, 6, 4, 1. And it turns out that these numbers are actually binomial coefficients. So the first one here would be 4, choose 0. This here is 4, choose 1. This here is 4, choose 2. This here is 4, choose 3. And the coefficient here is 4, choose 4. By actually plugging into this formula, you can actually figure out what those guys are. So if you find 4, choose 0, you get 1. Find 4, choose 1, you get 4. Find 4, choose 2, you get 6. Find 4, choose 3, you get 4. Find 4, choose 4, you get 1 by using that formula. So these guys actually give you the coefficients. And to find the powers of x, you just start with the highest power of x and count down. So you have the x to the fourth, x cubed, x squared, x, and x to the 0. And then you start with y to the 0 and count up, y to the 0, y to the 1, y to the 2, y to the 3, y to the 4. So you can actually expand things like that. So now the idea is, so that's binomial theorem. You would have learned about that in pre-calculus, although you probably never wrote it out as a summation in pre-calculus. But this is something you would have learned in pre-calculus class. Now, the idea here is we want to generalize this. So it turns out that you can actually convert this using Taylor series, and you can actually write this where the upper bound is infinite. And you can actually write out the Taylor series for this guy, and it'll actually give you the series for this guy, where it just gives you, whenever your n is an integer, it'll just give you zeros for every one above the highest power. But now when you generalize it and you allow your n to be any positive number, not just integers, and you use this same formula that's in green, something magical happens. So for example, you can just let n equals a half, for example. And so you'd have a half times a half minus 1 times a half minus 2 times da da da, all the way down to a half minus whatever your k should be. And then you can actually create coefficients just like in the binomial theorem. And you can actually prove that this converges to that, right? So for example, if I wanted to find x plus y to the 1/2 power, as I just mentioned, I would literally just plug in a half here for the n value. And so this would actually expand into, a half, choose 0, x to the 0, y to the 0. Sorry, x to the 0, x to the 1/2, y to the 0. Then you would get a half, choose 1. X to the 1, y choose 0, x to the, let's get these guys up. K goes from 0, so it's x to the 0 and y to the n minus k. So in this case, that would be a half minus 0 and so on, right? So you actually start to expand these guys, and you'll notice that you can actually get an infinite series from that. And for example, you'd be able to derive this, for example. So in the above, set y equals 1, and it'll actually expand into this guy. So you get an infinite series here, which means, for example, if I were to replace the x with an x squared, it would expand into this series here, right? And a very common mistake, that I even put this in my syllabus because it's so common, whenever students see something like this, they would tend to just distribute the radical across a sum, which is very wrong. And they'd write that as something like x plus 1, which is wrong on so many levels. It turns out that if you were to use two terms to approximate the answer, 1 plus x squared over 2 is actually a much better approximation than 1 plus x. So they're wrong in all sorts of ways. Even if you were to write two terms on this, these would not be the two terms. These guys are actually two terms. And you can actually start graphing these guys out, right? You can graph this on like Wolfram alpha and then graph this on Wolfram alpha. You'd realize that they're very similar. This here is a radical, so it's going to have a curve in it, whereas x1 plus x is a straight line. It's not going to fit very well, but this would fit very well. And the more power you include, you'll realize that it fits even better and better over time. So that's something you can try. So I just thought I'd mention how the binomial theorem would work. Like I said, you can go through and work this out. And I even put a few homework problems on them, but they're worth 0 points. Just something I thought you should be be aware of. And yeah, I told you here is something to try. So you can actually graph that and then graph each successive term of this. And you'll realize that the graphs actually start to fit closer and closer together over time. And it's really cool to actually see it. Yeah. Computing limits, we already spoke about. Actually, to try these for next time, we'll actually get to that. Before that, I also want to show you another thing that's cool that we can get from Euler's equation. So, for example, let's say I wanted to do e to the a plus bi, right? For whatever reason. So one thing I can notice here is that this is going to be e to the a plus b I. So what I can do here is someone got dropped. Okay. So here's what I can do. I can realize that this is the same as, say, e to the IA times e to the IB, just by laws of exponents. Then I can use the fact that I know Euler's equation. I can rewrite these two guys. So I could rewrite this as cosine A plus I times sine A. Over here, I can write this as cosine B plus I times sine B. I can now multiply out. So this is cosine A cosine B plus I times cosine A sine B plus I times sine A cosine B minus, because I get I squared, or let me just put plus I squared, sine A sine B. And did that multiply out correctly? Let me check. Cosine A cosine B, cosine A sine B, I sine A cosine B, and sine A sine B. Okay, yeah. So now this would become cosine A cosine B minus sine A sine B. So those are the guys without the i's. So it's this and this. And then the guys with the I can have cosine A sine B plus sine A cosine B. Okay. And does anyone notice anything with these formulas? Notice here, also by Euler's equation, this is actually the same as cosine of A plus B plus I sine of A plus B. And so notice what we just did. We just actually derived the addition formula for sine and cosine. Right? Cosine A plus B is cosine A cosine B minus sine A sine B. If you remember your trig, you'll remember that. Sine of A plus B is actually cosine A sine B sine A plus sine A cosine B, which is pretty cool. I actually derived these addition formulas for my pre-calc class. If you want to see in pre-calc class how it was derived, you can watch that video. It's a lot more complicated and a lot less motivated. So normally before this point, we'd use this complicated geometry. We'd like attach right triangles to each other in this weird way. Oh, imagine these two right triangles where the angle over here is A and this is B, and we stack them this way. And then you can use SOHCAHTOA and Pythagoras' theorem to figure out the addition formulas. And it was like, no one knew what was going on. But here, you can actually derive a lot of these formulas. It turns out a lot of trig formulas can come back to this. This is, again, just showing you some of the important ideas behind Euler's formulas. And it's very, very useful. You can go back and prove a lot of things in trigonometry and geometry much easier in this formula than you did the first time. So that was just something else pretty cool. What if we wanted to actually derive Maclaurin series for the hyperbolic cosine and sine? We could actually do that as well. Notice here, if I wanted to do cosh, for example, this is just going to be 1/2 times e to the x plus e to the minus x. Here I can actually apply a Maclaurin series, so we're still in the section of applications of series. E to the x we know by heart by now, hopefully. This is this. E to the minus x is this. Notice here we can start writing these guys out. So this one would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 plus, and that's what the first series looks like. The second series has an alternating sign. So it would start with 1, then minus x, then plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the fourth over 4 factorial minus dot dot dot. If you start to see what's going to happen here, notice that the odd terms will actually cancel out, while all the even terms will actually double up. So here you'd have 2 plus 2 times x squared over 2 factorial plus 2 times x to the fourth over 4 factorial plus dot dot dot. And you can cancel this half into all of those 2's, and you would end up with 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial plus dot dot dot. And what you'll notice is that this guy, you can actually write it as a series in this way. It's actually x to the 2n over 2n factorial. It's like a cosine, but it's better than a cosine. So notice that this is like a cosine. But no alternating signs. So this is exactly the cosine graph, the cosine power series, but for the cosh, the hyperbolic cosine, it's like a cosine, but not alternating. Who would have thought? It turns out the name hyperbolic cosine is pretty apt, right? Not only is it an even function, but it actually looks like a cosine. Why would they call it a cosine? Why wasn't this function called something else? It turns out it behaves like a cosine very much. So yeah, so not only does there's this kind of connection between the trig identities with these hyperbolic trig functions, but when you look at the actual series expansions of the hyperbolic trig functions and compare them to the series expansions of the trig functions, you'll see a lot of similarities there as well, right? So it's pretty cool. Yeah. Right? You'll notice a lot of things like that too. So you can actually derive that the cosh and sinh functions, their Maclaurin series looks a lot like the sine and cosine Maclaurin series, except there's no -1 to the n. Pretty cool. So if you know the cosine and sine by heart, technically you also know the cosh and sinh by heart in terms of power series. You'll be able to actually do that. So that was pretty cool. Okay. So that was all sort of like an informal thing. I decided to show you guys that because it was just pretty cool and you guys should kind of know about it. But I'm not going to specifically test you on any of this. But what I will test you on is like this. So this is the important thing. So if you're falling asleep or kind of zoning out, stop, come back, pay attention now. So this is the stuff that you really need to know how to do. Okay, so I'm going to test you on stuff like this. So right now we're back to the important stuff when it comes to testing. So be careful. It seems like Caitlin's having internet trouble, but hopefully you go. Okay, so again, just to remind you and make a note to self again. So of all these applications, the only one I'm really going to test you on is number 5. So that's what you need to know. Okay. Yeah. So all of these other things I mentioned, because 1, they're cool, and 2, there's going to come a point in your math classes where people are just going to expect you to know this stuff, and It's like it's one of those things where it's like, oh, you'll cover this in future classes, and then when you get to the future classes, it's like everyone will say, oh, you definitely knew this from your previous classes. It's one of those things. So everyone's going to kind of expect you to know it, and very few people actually go over it from scratch. So I thought I'd spend some time and talk about that. Very important stuff, very cool stuff. But you're kind of expected to learn them by osmosis at some point. So I thought I'd just quickly run over some stuff. In terms of what you definitely need to know for this class, where I'm definitely going to test you on, you definitely want to need to know how to use power series to evaluate integrals, especially when they're impossible to do by hand, or they're going to be very, very, very difficult to do by hand. And you should know how to approximate them, know how many terms of your series answer you would need to approximate to within a certain degree of accuracy. We've done problems like this before with things that we could connect to the series for 1 over 1 minus x. But now we're going to connect to other things. So we learned about Taylor series and Maclaurin series, sort of this general approach to finding power series. And so now we can, in theory, do that sort of maneuver, those sort of manipulations, even if we don't have something that we know how to connect to 1 over 1 minus x. So that's another very, very important application of power series. So we are left with some examples here that I ask you guys to try. So maybe at this point, someone can tell me what you actually tried for this. How did you find the Maclaurin series of sine of 2x squared?
Well, I started with the Maclaurin series of sine of x, which
is
x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, and then minus x to the seventh over 7 factorial.
Okay.
And then I just plugged in 2x squared every time there was an x.
Right. So I'd probably write it in this version here. So I know part B says you only need to do 2 terms, but part A did not say that. So you definitely want the more general term here. So that's sine of x. So yeah, so this means that if I want sine of 2x squared, I literally just go in and plug in 2x squared everywhere. So this is just going to be, and this is n goes from 0 to infinity. So this is going to be n goes from 0 to infinity of minus 1 to the n. And then I'm going to have here 2x squared. Just plug it in for x. And so now what you would have is just expanding. You have minus 1 to the n. You have 2 to the 2n plus 1. You would have x to the 4n plus 2 over 2n plus 1 factorial. And that's going to be your Maclaurin series. Right? So by knowing, and this is a sine function, so you should know by heart what the Maclaurin series for a sine function by itself looks like. And then you can actually just manipulate that. In the same way that if I knew what is 1 over 1 minus x, I could easily figure out what is 1 over 1 minus x squared. It just means everywhere I saw x, I now put an x squared. So same idea can apply here. So that is what part A would look like. So part B says, using your answer above, estimate this integral. So it turns out sine of 2x squared does not have an elementary antiderivative. Okay, so you can actually compute this general antiderivative by hand. It's impossible to write that in terms of any of the functions that we know about right now. So that's a non-elementary integral. Okay, so we know that the elementary functions, they're built up of those 6 functions: polynomials, radicals, rationals, exponentials, logarithms, and trig functions, and combinations of these and compositions of these all possibilities of ways that you can combine these functions to get new functions. These are called the elementary functions. And it turns out that there is no way to actually write down the antiderivative of sine of 2x squared using any of those functions. Right, so you can actually, it's literally impossible. No, I'm not saying it's difficult. I'm saying it's literally impossible to actually write down the answer to this in that way, right? We literally had to make up an answer here. Kind of like how when we wanted to solve the equation x squared equals 1, we literally invented the number I to be able to solve that equation. In that same way, to be able to talk about the integral of something like sine of 2x squared, we literally had to invent a new function to be a placeholder for that answer, right? So you can actually do it by hand. However, because I know the series, I can actually compute the integral. We know that this guy is absolutely convergent on the entire real line. And so I can integrate this series, I can differentiate the series, I can literally everywhere I see sine of 2x squared, I can replace it with this series. And so that is pretty useful when it comes to actually doing something like an integral. So I would be able to say that the integral from 0 to 1/10 of sine of 2x squared is going to be the same as the integral from 0 to 1/10 of this series. Then that's just the integral of an infinite sum, but we know that this is just the infinite sum of integrals because we have the law of we have the commutativity of addition for absolutely convergent series. So I can actually switch the series and the integral. I can do that because of absolute convergence. And now, when it comes to this integral, this whole thing here is just a constant because it has no x's in it. So I just leave it alone. I'm actually integrating something that looks like a polynomial, the x to the 4n plus 2, in which case the power rule applies. So that's just going to be, I'm going to leave this minus 1 to the n, 2 to the 2n plus 1 over 2n plus 1 factorial. This is going to be add 1 to the power and divide by the new power between 0 and 1/10. Now, of course, if I plug in the 1/10 into x, this is going to become minus 1 to the n, 2 to the 2n plus 1 over 2n plus 1 factorial. And if I plug in 1/10 in the denominator, this will become times 10 to the 4n plus 3 times 4n plus 3. Minus, when I plug in the 0, that just kills everything. So that's literally the series there. And so now it's said to, using the sum of 2 fractions, you don't need to simplify your answer. What is this integral? So now I just evaluate the first 2 terms. So then I just plug in, plug in n equals 0. If I plug in n equals 0, I would get 2 divided by 1 times 10 cubed times 3. Plus, if I plug in n equals 1, I would get minus 2 cubed over 3 factorial times 10 to the 7 times 7. Plus, now I'm going to do one more. That's already 2 fractions, but I'm going to do one more. If my n equals 2, I would get 2 to the 5th over 5 factorial times 10 to the 4 times 2 is 8 plus 3 to the 11. And if I plug in 2 there, that's times 11 minus dot, dot, dot. So this is going to just be 2 over 3 times 10 cubed minus 8 over 6 times 7 times 10 to the 7 plus dot, dot, dot. So according to just 2 fractions, this is my answer. So I'd be able to say this integral from 0 to 1/10 of sine of 2x squared dx is approximately equal to this, approximated with 2 fractions. So we have that. Any questions on anything? Okay, so now it says, give an upper bound for the error in your estimate above. Did anyone figure out how to deal with that?
Is it equal to the n equals 2 term?
How? Why?
I might be getting it confused with the other theorem that we did. It's like the first term not included in the approximation.
Right. What theorem is that? Anyone remember what theorem she's thinking about?
Alternating series approximation theorem.
It's the alternating series approximation theorem by the alternating series approximation theorem. So remember, notice here that this guy is an alternating series. And we're using S2 to approximate it. And we know by the alternating series approximation theorem, so this guy is going to apply down here, So it basically means that S minus S2, technically it's always S minus Sn. So S minus S2 is going to be less than or equal to the magnitude of A3, where A3 here is the third term. So this here is the actual value of integral. This here is your answer from above. So the difference between the two is the error. That's how wrong I am, right? So if I take my approximation above, which is this fraction here, and I subtract it from the real answer, there's going to be a difference between the two. That's the error. And because this is an alternating series, I know exactly how to find the error. The error is approximated by the very next term, which is why over here, even though I was required to find two terms, I still computed the third term. Because I kind of knew ahead of time that I would need it. Even if you didn't compute it and you went down here, you'll just know that based on this question, I need to go back and compute the very next term. So for alternating series, the very next term tells you how good you are to the actual answer. So this means the very next term, 2 to the 5th, over 5 factorial times 10 to the, was it 11? Times 10 to the 11 times 11 is an upper bound on the error. By the way, FYI, if you're curious, maybe I can actually. It's actually a pretty good approximation. So this is 2.42. This is 2.4242. And you're like, well, that's a lot. Well, no, it's times 10 to the minus 13. So by adding up these two fractions, you're actually accurate up to 12 decimal places, which is crazy. So yeah, impossible to integrate. However, Wolfram alpha would only need to add up 2 terms of this guy to tell you what the answer is to 12 decimal places. Literally only 2 terms, right? So while you're like, man, Wolfram alpha is like pulling some crazy Riemann sums like acrobatics on this guy, and nope, it just converted it to a power series, added 2 terms. So when you're thinking Wolfram alpha is doing some like complicated integration, it's actually just adding 2 fractions. And these would be the 2 fractions it wants to add. So if it's giving you the answer to 12 or less decimal places, that's going to be the answer. So for this particular thing, it's pretty accurate. And that's because when you're close to 0, the sign is bouncing up and down when you're squaring the x. So it's, yeah. It's just oscillating very fast. So yeah, you don't need a lot of terms. Yeah, so that was that one. So like I said, this kind of question is a very important kind of question. I'll be asking you some or all parts of a question like this for sure on like a quiz or a final or a test or any of that. It's a very, very important application. That being said, we can do the other one. Well, this one again is just going through the motions. How you actually would, again, for those of you who've done probably in statistics, how you would actually compute something like the probability for a certain range under a normal distribution. You could do it very similar to this. So when you look up the normal distribution values in your table of integrals, like how do they know what values to put? So it could be this. They could actually just compute all the values by doing this. So the equation of a normal distribution is an equation. It's a shifted version of e to the minus x squared. So when you want to find like the area under that curve, you have to integrate that. But e to the minus x squared, once again, has no elementary antiderivative. So what you can do, though, one game in town, one of the best games in town, to actually get a handle on something like this, is to just replace it with your series. So in A, we know that e to the x is this series. So this means that e to the minus x squared is going to be this series. And B, if I wanted to figure out the integral from 0 to 1 of e to the minus x squared, then I could just realize, oh, that's the same as integrating this series. And that's the same as if I were to switch the series and the integral. Because of absolute convergence. In fact, I have absolute convergence for all x values here. And that is just integrating using the power rule. So now I went from literally an impossible scenario, like I'm in an impossible situation. But we figured out how to actually get through it a lot easier. So I'm going to leave this guy alone and then add 1 to the power, divide by the new power. If I plug in 1 into x, then the top just becomes 1. So this is minus 1 to the n over n factorial times 2n plus 1. If I plug in 0 into x, everyone goes to 0. And so what I can say is this is going to be approximately equal to, to start plugging in terms, my n equals 0 term, my n equals 1 term, my n equals 2 term. So if I plug in n equals 0, I would get 1. Plug in n equals 1, I would get minus a third. Plug in n equals 2, I would get 1 over 10. Looks like that's 2 times 5. Yeah, minus dot dot dot. And so this means this guy is approximately equal to 1 minus a third using a sum of 2 fractions. And if I were to ask you, how good is this approximation? What is an upper bound on the error? Well, an upper bound for the error, well, that would just be by the alternating series approximation theorem. Because again, it's an alternating series. S minus S2 is supposed to be less than or equal to A3. And here, A3 is equal to 1/10. And so 1/10 or 0.1 is an upper bound on the error. You'll notice that this is a lot less accurate than the other series, but that's because it's an exponential. Remember, exponentials grow really fast. So the amount of change that will happen between 0 and 1 is large compared to what it would be for a sine function. So we can only get away with like 1 decimal place here. But that's just because it's the nature of the exponential function. But yeah, just went through the full process for a problem like that. So something like that, you definitely need to know how to do. I'll definitely ask you how to do something like that. So any questions on that, on this process or anything? Yeah, so if you already know a Maclaurin series, I expect you to be able to develop Maclaurin series of anything similar enough just by plugging in stuff. And so I told you the Maclaurin series that I expect you to have memorized. You should also know how to build up a Taylor series from scratch, which I demonstrated with e to the x and cosine of x. So I might ask you to do things like that as well. But yeah, and this is a very, very important application. We can use it to compute integrals. And we can just use enough terms to get the desired accuracy. So for those of you who are in a probability book, basically they just make sure to use enough terms to get it correct to 4 decimal places or whatever they want to use in the table. Okay. Now, of course, in a class like probability, they'll just tell you to look it up in a table because they don't want you to do this by hand every time when you're looking up a z-score, like the probability for z less than something. Yeah, it'll take too long, but knowing what happens and how you could get to such an answer is useful. So that's the end of this section. What we're going to do now is we're going to kind of wrap up with series. So again, here, it's not. So again, here, I'm not going to strictly test you on anything in this section. I do expect you to know some overall key facts, like knowing about just some general ideas about the relationship between a function and a Taylor series generated by the function. Things like, if I create a Taylor series based on a function using that formula, is that Taylor series always representative of the function? Can I always just swap them out like I just did, right? So if I wanted to integrate f of x, is it always the same as the integral of the Taylor series of the function? So questions like that, I'd expect you to know. How good is a Taylor series as an approximation to a function? So this goes into the idea of, I can make this a little bit bigger, about like the convergence of Taylor series. So I just want to talk about some essentials of that. So yeah, basically you can generalize the mean value theorem to get something that's called Taylor's theorem. So it's basically saying that if all the derivatives exist, then you can create something that's called an nth degree Taylor polynomial like this. And there will be points A and B in an interval such that this is always true. Don't need to know this. Okay. And you can compare to the mean value theorem and realizing that mean value theorem basically says this equation is true. It turns out Taylor's theorem says this equation can be extended even further with the uses of derivatives, right? So here's an important part. You can think of a Taylor series as just that guy, so the nth degree Taylor polynomial, plus a remainder term, which I actually mentioned to you before. And it turns out that the remainder term can be written in this form, again, by the above formula. And again, you don't need to know this either. If you're a math major, there's going to come a point where they're going to expect you to need to know this in detail. But for us, I'm not going to like test you on this. However, the part of the formula in front of the Rn, this is called the nth degree Taylor polynomial centered at A. And this you need to know. But it's not anything crazy. It's literally just using the Taylor's formula that I told you about Taylor series, but you only do it for a certain n. So I can ask you, find the third degree Taylor polynomial. And pretty much what you do is you take the Taylor series and you write out up to the power x cubed, right? You actually just write it out. And that's basically it. So remember, so you can think of a function, Taylor series of f this is just the series, n goes from 0 to infinity of f to the nth derivative evaluated at x naught times over n factorial times x minus x naught to the n. Now, if you were to start writing this out, it's going to look like f. I'll probably need a little more space here. If you start writing this out, it's going to look like fx0 plus f prime at x0 over 1 factorial x minus x0 plus f double prime at x0 over 2 factorial times x minus x0 x naught squared plus dot dot dot, and you keep going dot 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 up to a point where you're at the nth degree, right? So you have x to the n evaluated at x naught over n factorial times x minus x naught to the n. And of course, you can actually keep going, right? So you'd have f to the n plus 1 evaluated at x naught over n plus 1 factorial x minus x naught to the n plus 1 plus you can have f to the n plus 2 evaluated x naught over n plus 2 factorial times x minus x naught to the n plus 2 plus dot dot dot. You can just keep going because it's going off to infinity. Now this part of the function here, up to degree n, this is called the nth degree Taylor polynomial. So this is what we refer to as t sub n of x. It's called the nth degree Taylor polynomial. For f of x. The guy that's left over from this point onwards, this is called r sub n, the remainder term. So if you know about the general formula of a Taylor series, and I ask you, oh, find the nth degree Taylor polynomial, it just means you just take that formula and just write out the first n+1 terms. Yeah, so that I would expect you to know. So I can ask you, okay, here's f of x is the square root of x. Write down the third degree Taylor polynomial. And what I expect you to do is find the derivative centered at 0 or something like that, or centered at 1. So I'd ask you to find the derivative, plug in 1, find the second derivative, plug in 1, find the third derivative, plug it in 1, etc. And then you're going to write this out and go all the way up to x minus 1 cubed, and then you'd stop. Now, here's the important part. If you look at this part, the blue part, and you notice that it approaches 0 as n approaches infinity, then on some interval, then it says that the Taylor series generated by f, meaning this series, it actually will converge to f. And what that basically means is that your function can be thought of as the Taylor series. Okay, so this I would say you should know. No. I would say you don't need to know the form of this, but you should be able to figure it out. Don't need to know the form of this, but you should know this idea. If the remainder term approaches 0 as n approaches infinity, then my Taylor series is equal to my function. And that's when I take off all terms, right? So if I go off, take the entire Taylor series, it will converge to the function. The more terms of the Taylor series I take, the closer and closer it gets to the function. And if I take all infinite number of terms, it is equal to, as in I can't tell the difference between this function and not. Something like this happens for e to the x, it happens for sine of x, it happens for cosine of x, it happens for 1/1 minus x, basically. And that's why I could interchange them. Is because if I were to write out the remainder term and take the limit of that as n approaches infinity, I would get 0 for all the functions that I mentioned before. Right? So that basically is this, which I would say, yeah, this worth knowing, right? Just as an idea, right? When can I think of a function as its Taylor series? Well, it's whenever the remainder term approaches 0 as n approaches infinity. Right, so I mentioned here, that's the key takeaway. So while I don't expect you to know about all the technical mumbo jumbo, I do expect you to know that as an idea. It's an important idea. So you might have the question, well, how do we know if the remainder term approaches 0? And there's another theorem that says that. It turns out that we know for sure that this is a bound of the remainder theorem. If your n plus first derivative is less than or equal to some positive number m, then your remainder term would be bounded by this inequality here. So in the case of sine and cosine, taking m equals 1 is going to work. In the case of e to the x, taking m equals, it looks like here, e to the d power would work. And so once you know that your remainder term is less than or equal to this, and clearly if m is a number, and you're divided by n plus 1 factorial, the limit approaches 0 as n approaches infinity. And so that's what happens with those two functions. Now I want to talk a little bit about when Taylor series goes wrong. Right, so a lot of you might find that, well, you should. Taylor series is a very powerful tool, but it doesn't always work and it doesn't always help. So for example, it's possible for functions to not have Taylor series at all. For example, this function, he doesn't have a Maclaurin series. How do I know he doesn't have a Maclaurin series? Well, it turns out that the third derivative does not exist at x equals 0. So this is a function that is not infinitely differentiable. Of course, because my f prime would be 3 absolute value of x squared. My f double prime would be 6 absolute value of x. My x triple prime would be, well, we know that absolute value of x has no derivative at 0. So f is not infinitely differentiable at 0. Which means doesn't have a Taylor series. So I mentioned in the last class that as long as we can just keep differentiating a function, you can find a Taylor series for it. Whether or not that's useful is another story. But I know a lot of students back from Calc 1 would feel like, can I do that with anything? So Calc 1 was a very easy, idealistic world where it's like every function we ask you about, yes, you can differentiate it forever. It's very nice. Turns out real life is a little bit more complicated. Not every function you come across, you can differentiate infinitely often. There are some functions that will have trouble. Here's one of them. And it's not even that complicated a function. Cube the absolute value, and now you have a function that's not infinitely differentiable at 0, which means you can actually write down a Maclaurin series because f triple prime, the derivative from the third derivative onwards don't exist. And it's not like they don't exist in that they're 0. It's like they don't exist in that they're not mathematically computable. So doesn't have a Taylor series. It's also possible for the coefficients to get too big. That would be an issue. So there are times when you can find a Taylor series, but it's not very useful. For example, let's say I have a function, and I can't really tell you about a function that has this property because it would be a non-elementary function. But suppose you had a function, I think it's easy enough to actually imagine that this were true, where the nth derivative evaluated at 0 it always gives you this number. So when I differentiate the first derivative, plug in 0, I get 1. The second derivative, plug in 0, I get 4. The third derivative, plug in 0, I get 36, right? So pretend I just have a function that does that. It's not very strange to think of a function that does that. Then the Maclaurin series would look like what? It would be the series n goes from 0 to infinity of n factorial squared over n factorial times x to the n. So this means the Taylor series for this, or the Maclaurin series for this, would be n factorial times x to the n. It turns out it's a very easy exercise by the ratio test to show that this diverges for all x except 0. Ratio test shows this diverges unless x equals 0, which means here's a Taylor series, but it only makes sense at this one point. So you have a Taylor series that literally the series only works here. Okay, not very useful. You're just telling me at x equals 0, the output is 0. Whoop-de-doo, doesn't really tell me anything. So there are times when you can't even find a Taylor series in the first place. There are other times when you can find a Taylor series, but it's not very useful. There are other times when you can find a Taylor series and work everywhere. However, it's still not useful because it converges to a whole other function. It turns out here that f to the nth derivative evaluated at 0 is always going to be 0, which means the Maclaurin series here is just the series of 0 x to the n. So just 0 plus 0 plus 0. So it works on the entire real line, but it is 0 on the entire real line, which means my Maclaurin series is actually the graph here. Which, yes, if I'm in this window, it's a pretty good approximation, but outside of that window, it's useless, right? So the Maclaurin series, it literally converges to a different function other than the one I started with. I can start with this function, and I can find a Taylor series, and it works on the entire real line, but the series actually converges to the 0 function. So to get a Taylor series to work, it's not as hunky-dory as you might think. There are times when it can't be even developed in the first place. There are other times when you can develop it, but it will work at a single point on the real line, which is not very useful. There are other times when you can create it, but it will converge to some whole other function other than the one that you started with. This is equivalent to getting f of x equals 0. So it's not very useful to approximate that function unless you're within a very small window. So there are times when you can things can go wrong for Taylor series. And I know we're about 10 minutes over time, but just one more cool thing I want to show you. So out of everything I just said, I think some like what I wrote in the green box here is what you definitely need to take away. So if I were to ask like a select which statement is true, or a true or false statement on a quiz, I can ask you something like, does every function have a Taylor series? And you should say no, or no, that's false. Or I can say something like, suppose a function has a Taylor series. Can we use this Taylor series to represent the function? The answer should be no. Again, because you know this. Or I can say something like, okay, a function has a Taylor expansion where the remainder term approaches 0. Can the Taylor series be used to represent the function? The answer should be yes, right? So things like that, I expect you to be able to tell me. Just to wrap up, there are a lot of links here that I'll leave in the notes for you guys to actually check out. But I feel like I should only show you like one of them just because it's pretty cool just to have like a visualization component to this. And I think I'd want to show you in the browser here. So just bear with me. It'll only be like 2 more minutes. But I think it's worth it. It's pretty cool. Let's see. Okay, so I clicked on the first link. Desmos.com, and it brings here. Hopefully you guys can actually see this on your screens. So here is the graph of y equals e to the x. Here's n. It tells you how many terms of the Taylor series I'm getting. So if you were to find the Taylor series of e to the x, you'll realize that the first term is 1. So this is just the constant function 1 when n equals 0. However, I can show you when I keep using more powers, what actually starts to happen. So I can play this here, and you see as the powers grow, the Taylor series gets more and more closer. You just actually see the red is the Taylor series. So the red would be actually the graph of y equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. And this goes all the way up to 20. So it goes all the way up to plus x to the 20th over 20 factorial. And as you can see, as you're going further and further, the red graph gets closer and closer to the green graph, the black graph. However, as you can see, if I were to stop this at say n equals 9, it fits the curve very closely here, but then outside of this window, it doesn't fit it very well. To actually fit the exponential with a polynomial, because of n behavior, I do need an infinite number of terms. Here's another one, this guy. So without, let's move this back. So here it looks like the bell curve, kind of like you'll see in a probability class. Actually, go in. And you'll realize here that if I now were to play that, the polynomials are getting closer and closer and closer to the curve, the higher the power I take. Right, so that's pretty cool. If I were to look at the sine function, notice that I can take polynomials approaching the sine function. So the red is the Taylor polynomials. So I'm just getting a bunch of odd functions. You'll notice that one side goes off to infinity while the other side goes off to negative infinity. And that's because it's always being an odd polynomial. But as you can see, the higher the powers go, the more it weaves closer and closer to the sine function. I can do the same thing for the cosine function. Right, you're weaving closer and closer and closer. I can do the same thing for the ln function. So notice that it just gets closer and closer from both sides to the function ln. And so if you were to use the Taylor series for this, I think if you actually write this out, it shows you the Taylor series for ln of x is this. So that's what's being plotted in red, and n is going up to 20, but you can actually change it. You can actually play around with this. It'll be pretty cool. Type in your own function, type in what you got for the answer for the Taylor series, and you can actually see it converging to the function. Whenever your remainder term approaches 0 as you go up to infinity, this is what happens. The red curve just consistently weaves itself and conforms to the actual graph, which I think it's pretty cool that you can see that. So you can play around with that, play around with some of the other links in the notes as well. So that ends series. So I will see you guys tomorrow doing the recitation section, and we'll talk about the next topic, which is from now on, all the topics, they aren't going to be that bad. Very basic. They're going to start from the beginning. The next topic is going to be parametric curves and polar coordinates. That's the third phase. We'll talk about that tomorrow. But this ends series. Homework for series is put up, so try to do those. Until then, I will bid you guys farewell. So thank you for your time and attention. Hopefully you have a good night, have a good rest of your week. Good luck with finals week coming up, and I will see you guys in the next one. Ciao.